All right. Not this one. Okay. Ooh. All right. So welcome to 209 AS Spring Edition. This is about computer architecture and security. And today I'm going to talk a little bit about kind of logistics, what you should expect from this class. And then we're going to start a little bit of kind of like a background information, and depending on our progress, we might actually kind of do a little bit more of a lecture because there are lots of things to cover. So as the pictures kind of suggest, the idea is, we're going to talk about computers and how we build computers, but we're going to also mainly talk about security as well. So as I said, the plan for today is a brief introduction of things that you can expect from this course. A little bit of admin trivia, some questions that you might have. I'm going to answer those, and then we're going to start some basic concepts. So I mean, the fundamental question is that we're going to get into in this course is hardware safe? And then the interesting thing about this is that it's a very tough question to answer. It's not like straightforward yes or no answer. And an interesting thing is in order to answer this, we have to kind of like think about various different things in terms of kind of like what's the formal definition of security, what are the assumptions, what are the goals of the attackers, and so on and so forth. And if I want to give you kind of a short answer to this question, the short answer is that for the longest time, we always thought that hardware was secure. So many of the things that we do when we were designing computers in early 80s, 90s, and early 2000 was based on this fact that, okay, hardware is something that you kind of like, there's some specification, you build it, you give it to the user, and that's it, right? And what would happen is like then there was a whole bunch of these kind of level of operating system and software and things like that on top of it. And then all those things were not really secure. There were a whole bunch of attacks that could happen on those systems. But we thought that the hardware, at least the part that's kind of like nothing can be changed in hardware. What we're going to see in this class is actually that part is no longer true because there are tons of attacks that can happen in hardware. We're going to particularly stay in the kind of like architecture and CPU level. We're not going to go really deep into the hardware. But we're going to talk about kind of these different attacks. And as you will see, most of these attacks actually kind of very new. So most of the papers and concepts that we're going to kind of cover starts in like mid 2010s and so like 2014, 15. The big kind of breakthrough in computer architecture security happens only a few years ago in 2017 to 2018 when there's kind of these transient execution attacks happens. And now it's kind of we open a big can of worms, and then the worms are coming out, and now we need to fix them. So that's kind of where we are at the moment. But in order to get to that point to talk about security, kind of half of this class is actually non-security related, and we're going to mainly just talk about computer architecture. And we're going to talk about advanced topics in computer architecture. So the assumption is that you have kind of taken some courses in preliminary computer architecture, and so you know a little bit about, and then we're going to talk more about that. So we're going to mainly talk about three main things: performance, which is kind of, if you have taken any course in computer architecture, you know that's the number one priority in any systems that we build is performance. But we're going to talk a little bit about overheads and power as well. So these are the things that we're going to focus a lot. And you will see that the reason that we are focusing on these things is that these are the very reasons that we have non-secure systems. So to kind of like in our pursuit to achieve very high performance systems, we actually introduce this security box to the system, unfortunately. And we're going to talk about kind of like how those things kind of generated, okay? And as I said, our focus would be on this kind of like computer architecture level here. Let me see. We're gonna mainly focus on kind of this side of things, okay? And mainly actually kind of here, these two parts, the microarchitecture and instruction set architecture. We're not gonna really go into the details of hardware, so you're not gonna see gates or RTLs and stuff like that in this course. And you're not going to see much of software development in this course. Actually, well, your computer assignments would be all software computer assignments, but the core of this class would be about this kind of layer in between. So the kind of the software, hardware co-design, the kind of the layer between these two. Okay, so it's kind of like the expectation of this, and this is what I'm showing here is abstraction layers of a system that start all the way from the physics all the way up to the application. So we're going to focus mainly on this part here. Okay. Let's see. Let me make this a little bit. Okay. But as we will see, is that security specifically is kind of very cross-layer topic. So it's not like really just the architecture that we need to think about. Architecture talks to the hardware, architecture talks to the application and software and the operating system. So we need to talk a little bit about those. But as I said, the main focus of this course would be on the microarchitecture layer. How do we actually build these components, put them together? How do we make them faster for kind of first goal and for our first focus, and then why making these things faster creates these problems. That would be the second thing that we're going to talk about in this class. Okay, so as I said, we're talking about kind of like two main things: secure and advanced computer architecture. The computer architecture part is kind of the common theme between the two. We're going to first talk more about advanced, and then we're going to talk a little bit about secure. Okay, so the format of the class is if you have taken courses with me, which looking at faces most of you have. So the class format, this is a graduate class, right? So it would be mostly, so I'm going to give you lectures. The first few weeks, I'm going to just give you lectures. But starting week 5, we're going to do paper readings and paper presentations. So like week 5, 6, and 7 is kind of you do most of the paper presentations. And then I'm going to also take over again and then do a little bit of lectures again in week 7. And then week 8 and 9, again, going to be some paper presentations. So there won't be much of it like a quizzes and exams. There will be just one final exam in week 10. Rest of it is, and there's also not homework. It's mostly just for you to kind of figure things out. So we're going to give you 4 computer assignments. The computer assignments we're going to talk about is a little bit different than other type of computer assignments that you've seen. But the idea here is that I want you to kind of become self-motivated and kind of follow the things that you're interested in. Again, if you've taken courses with me, that's kind of the same strategy, same mentality that we have in the past. If you have taken undergrad course with me, but not grad courses, on undergrads, the class is more kind of like, lectures, quizzes, homeworks, but this is more of like, we're going to talk about topics. The first few weeks going to be like a classic undergrad course, but then after that, we're going to do more of a paper readings and discussions and so on and so forth. Okay. So let's talk about logistics. So how many of you haven't taken the course with me before? Okay. Yeah. A few haven't. Yeah. Okay, so my name is Nader. I started at UCLA in 2020. This is my 4th year here. I do mostly computer architecture, of course, and mainly security. So this is kind of basically what I do for my research. And my background is like I got my bachelor in electrical engineering, but I got my PhD in CS. So it's kind of like, that's why I'm kind of in between these two. If you have taken course with me, you're probably familiar with these two guys. These are my cats. This is Meadow, this is PJ. You're going to see a lot of cat photos in this class. That's kind of the signature. The ways to contact me is you can direct message me on CampusFire. How many of you haven't enrolled on CampusFire yet? Okay, please do. How many of you haven't used ever CampusFire? You're not familiar with CampusFire. Okay, so CampusFire is this website that it's kind of like Piazza. Have you used Piazza before? Exactly like that, a little bit nicer. So just enroll. So I posted the link and the join code on BruinLearn. Just go there, copy on the link, and go there and enroll. We're not going to use BruinWalk in this class. We're going to use CampusFire. CampusFire are going to be used for kind of asking questions and answering questions, stuff like that. Easiest way to contact me is also direct message me on CampusFire. Okay. If there are more, important issues, you can email me at this email address. I have office hours right after the class on Wednesday, 4 to 5. My office is in Bolter Hall, just right across, and in 6th floor, 6731G. And you can just come to my office hours. I usually also free on Friday afternoon, so if Wednesday doesn't work, most of the time I'll be there. But if you want to make sure that I'm there, you can just shoot me an email or message me on CampusWire, and we're gonna talk. If none of these times work for you, or if you're watching this recorded version and you cannot come into the class, send me a message. We can either find another time or we can schedule a Zoom meeting, something like that. Okay. So for you guys to kind of know each other as well, I recommend you to look at this website. It's called Padlet. Again, those of you who have taken course with me are familiar with this. If you're not, just scan this code and add your kind of short bio of what you're interested in, so that we know each other a little bit more. I think I already put mine, but feel free to add yours as soon as possible. This is optional, but it would be nice to kind of get to know you, because part of this class is also we know each other. Especially I'm very interested to learn more about you. So feel free to share, feel free to kind of like stop by, chat with me. I'm very interested to learn more about you guys. All right, so let me talk about course elements. Any questions so far? Good. Okay. So course elements. So there will be 5, 6 different elements. So there will be obviously the lectures. Then there are paper readings and presentations. It's not much of a reading, it's mostly presentations. Then the participation in the class. There is an exam, a final exam. There are computer assignments or championships that I'm going to describe what they are. And there is a final project in this class. Okay. So let me go through one by one. So as I said, the lectures, the first few weeks, I'm going to mainly focus on kind of advanced microarchitecture design. So we're going to talk about an analog order processor. Specifically, we're going to talk about a recent RISC-V processor, and we're going to kind of break down every single part of it, and we're going to discuss various different things in it. So we're going to mainly focus on kind of high-end analog order execution, which is kind of the state of the art. And then we're going to start talking about security issues. And that's where we're going to mainly focus on paper readings and paper presentations. So I will give you kind of a short overview of the attacks, but the majority of the content will come from the paper presentations. What we're going to do is that we're going to do 5 or 6 paper presentations per class. But the way it's going to be doing it is that I'm going to give you kind of a quick overview at the beginning of each session of like, these are the papers that we're going to talk about. And I'm going to break that down a little bit once the students are going to present those papers, okay? But the first few weeks is just a regular lecture class, okay? And as I said, the most things that we're going to focus on would be out of order executions and various topics on that. We're also going to talk a little bit about memory hierarchy, especially cache and DRAM, because lots of these security issues is basically on the memory side. So we're going to talk about things such as rowhammer attacks, cache side channels attacks, and those kind of things. We're also going to talk about performance related, how we actually make memory systems more performant in an advanced systems. We're going to talk about those as well. Important things that you have to remember is that this is not an introductory course in computer architecture. So if you haven't taken any computer architecture course before, this is probably not a good course or not a good class for you to take. Okay, what you can do, and by the way, I'm going to talk about a little bit of kind of what we're expecting a little bit later, and then also wait for next class, end of next class, because I'm going to review topics in the next class and see how much of that topics you kind of know. If you know more than like 50-60% of it, then you're good. If you have no idea what I'm talking about, then again, this is another indication that this is not a good class for you. Okay. So in order to kind of again know what you know, so you have kind of 2 things you can take a look at. So I teach an introductory course, an undergrad level course in computer architecture, ECE 116 or CS 151, which I teach on fall. You can actually go to the website of this website here and look at the lectures and look at the syllabus and see how much you know about that. Essentially, what you need in order to understand the topics in this course is anything up to lecture 8 of that class. If you kind of cover most of those things and you feel comfortable about those contents, then I think you're good to go and you should keep this class. If you think you're lacking a lot, if you really want to keep this class, you can actually try to catch up. So you can watch those videos. All the videos are available online. You can watch them this week and next week, maybe, to catch up if you want to, or you can consider taking the introductory class either now or next fall or next winter or whatever, and consider taking this class again next year if you're not graduate. Okay. So, but this I want to emphasize is that we're assuming that you have some fundamental knowledge about computer architecture. Okay. Otherwise, it would be tough for you to kind of follow along. And again, if you're not 100% sure whether or not you know those things, you can wait until next lecture on Wednesday to kind of decide whether or not this is a good class for you. Okay. Questions? All right. So everything about the class is actually available online on this website here. So if you just go to, there, you will see it. One thing that you can actually check out as well is if you actually change this, if you actually go into here, you will see the list of all of the classes that I teach. And then, for example, if you want to find that computer architecture class, you can go and find it there. All the previous versions are available there. This is the first time we are teaching this class, so there is no prior material for this class, obviously. But again, for the introductory class, you can find information there. So this would be for all the lectures and videos and exams and homeworks. Everything will be posted in this website. Then there is CampusWire for all the announcements, the questions, discussions, and so on. So if you have any questions about any of the lectures or homeworks and anything like that, post it on CampusWire. Please enroll as soon as possible. And then we won't gonna use Canvas anymore. So if you don't see any announcement, it's because you're not enrolling the right website. And then we're gonna use Gradescope for submitting the assignments and submitting the exams. And you should be already auto-enrolled. I'm gonna kind of I usually kind of update the list because people dropping and adding. But if by next week you're not added into Gradescope, let me know, and then I'll add you individually. Okay. So all the lectures would be in person, but I'll also record everything. And that's why actually you see that not many people are coming to the class, because they just really love to just sit at home and watch them. You can do the same if you want to. So attendance is encouraged but not required. If you feel like you kind of learn more by watching the videos, feel free to watch it. Generally, I recommend you to come to the class for two reasons. One is you can ask questions, and then second is you can actually have interactions, and then you can always have the videos to fall back into, right? So you can always watch the video whenever you want to. So try to come to the class, but if you don't want to, that's okay. You can watch the recordings. Okay. So the syllabus is actually also posted on the website. As I said, we're going to range, different topics. We're going to talk about, mainly we're going to talk about out of order execution, backend and front end, and then start security concepts and a little bit of memory systems and caches and so on and so forth. So I already talked about this, so let me move on. But kind of like a quick disclaimer is that I might change a little bit of move around topics a little bit, so don't be surprised if I did that, because this is the first time we're teaching this, so I need to kind of gauge the speed and the level of difficulty and things like that. So I might add or I might most likely remove some of the things. All right, so paper presentations is a very important part of this class. As I said, it's going to start in week 5. So there's those of you who've taken course with me, there's a slight change in the presentation formats. We're going to do like 5 or 6 presentations each week. We call it group. And actually, the list of the papers we want to present is on the website. You can go and check it out now. So you will see that it says like G1, G2, all the way to G7. So these are different groups of papers that we're going to talk. These papers are kind of all about the relevant topics. So for example, group 1 is about cache side channel attacks. Group 2 is about cache side channel defenses. Group 3 is about transient execution attacks. 4 is about defenses. 5 is about roll hammer attacks, 6 is about memory safety and hardware, and the 7 is about trusted execution environment. So these are different groups. And as I said, what we're going to do is that for each group presentation, I'm going to first kind of give you a brief overview of the topic. Then we're going to do the presentations, and then afterwards, I'm going to also kind of like, break it down a little bit for you. Okay. Each person has to, present at least once in the class, once and only once. We're going to do a group of 1 or 2 because there are more papers that we want to present. I think last time I checked, there are 55 plus 5 on the wait list, 60 students in the class. I think the room capacity is 63. So probably kind of dance around somewhere between 50, 60 students in this class. I'm assuming, because there's always like kind of some people drop, some people take. So for 50 students, we're going to have 7 different groups and 5 papers each, 5 or 6 papers each. So we have around 35 to 37 papers, which means that most of the groups would be individual. There will be some groups that has to be 2 people because we have 50 people at least. Okay. So there is a sign-up sheet on the website. There's a Google form. If you go there, you will see that there's a sign-up sheet that you can actually select which groups you want to present. You don't need to select individual papers, just select the groups that you're interested in, and try to select multiple so that I can kind of give you a better assignment. If you have a teammate, you can have one teammate, list their name in the Google form as well. As I said, it's not going to be guaranteed that I'm going to pair you up because not everybody going to have a team member. But what I'm going to do is that I'm going to try to do that, and I'm going to do first come first serve kind of thing. So if you submit it early, there's more chance that you're going to pair up with someone. And then I'm going to assign one of those kind of 5, 6 papers in that group randomly to you. And then we're going to announce the presentation schedule and presentation list on hopefully end of this week or early next week. You can actually already see when is the time for presentation. So if you have like conflicts and stuff like that, you can avoid selecting those dates if you want to. Presentations would be around 15 minutes. So like 5 or 6 we have each week, each session, so that we have the full 1 hour and 30 minutes kind of like, presentation time. So the goal of the presentation is that, as I said, this is a very researchy topic, especially the security side of things. So we're going to actually get familiar with the list of kind of back-to-back papers to kind of understand the state of the art in that particular topic. So kind of the idea is going a little bit deeper and focus on that particular security problems when we do the paper presentations, and everybody else kind of gets an idea about what that paper is about, what that concept is about. And then hopefully once they see 5 or 6 of them and back to back, they will get a generic idea of that field and the security problems in that field, right? For example, CAC side channel attacks or defenses and so on and so forth. Okay. Try to kind of like be, doing a good job on the presentations. The presentation, of course, will be graded, so it's probably part of your grade. But since it's kind of like, everybody going to listen to your presentations, the better the presentation is, the more understanding helpful for everybody else as well. You're going to be judged on 2 things, on your presentations and your content. So it's not just the content or slides, it's also the way that you deliver it is important for us. And then, of course, as I said, the important part is, you try to use good visuals, try to spend time on the content, and try to practice it so that you can have a good presentation. I kind of like, I can go, I mean, these slides will be here. So whenever you're designing your presentations, please go back to this slide, page 27, and look at these kind of guidelines. Essentially, the idea is for you to read a paper in more depth. So that's kind of number 1. So you're going to read a little bit more about that particular topic. You're also gonna, practice your presentation skills and receive some feedback. And then, of course, for the other students would be kind of learning about those papers. And then, I mean, if you find some teammates, it's not gonna apply for everybody, but for some of you, it's also you might, meet new people and talk to people. So as I said, 15 minutes. try to stick to 15 minutes. Don't go over it. Under it, if it's like, 12 to 15, that's fine. Don't go below 10, because again, that means that you didn't really prepare enough material. So try to kind of stay between 10 to 15, closer to 15, but not above 15, okay? And then try to follow these guidelines. Again, these will be here. Things like, try to not kind of like talk about the motivation of the thing, because as I said, I'm going to give a brief overview of the area at the beginning. So everybody will be already familiar with why, for example, what is the importance of the attack and so on and so forth. Try to actually talk about specifics of that paper, okay? And then try to also use the lectures to convey your message, and then kind of build on top of that. So kind of like, reference to the lecture and say, okay, we talked about this in the class. What this paper is going to talk about is kind of addition to this thing that we talked in class, okay? So make sure that you watch the lectures before preparing your presentations, because sometimes the problem that I've seen before is people don't really watch the lectures and start explaining things that we already explained in the class. So make sure that you're up to date when you're presenting your papers, okay? And then, as I said, focus on the specifics of the proposed solution in that paper, the new thing in that paper, and don't kind of focus on things around it, okay? We're not really, the result part of the paper is not that much important for us. So don't spend too much time on like showing this graph and that graph and saying, oh, this one 10% better than the other and so on and so forth. You're here mostly for getting the gist of the paper, the big picture of the paper. That's what we're going to remember at the end. If somebody's really, curious about the numbers, they're going to go and see the, the numbers themselves. So don't focus mostly on the new concept, the innovation, the novelty, rather than kind of like the numbers. And then one thing I want you to do is kind of like have one final slide to talk about kind of your thinking about this paper, the discussion points that you think it might be interesting. Because then again, once we do this 5, 6, then we're going to have a nice kind of like set of topics that we can talk about a little bit more. Okay? So what I want you to do is that in order to make the presentation and grading a little bit easier, I'm going to create like a Gradescope assignment. The day before your presentation, please submit your slides there. If you are two people each individually have to submit. If there's like one person, that person has to submit the slides, and then I'm going to provide the feedback on that Gradescope. So this way you can actually receive the feedback. Questions? Especially for new people. Questions? Good. Clear? Good. All right. Great. So as I said, participation is encouraged. There won't be any grades for it. Try to ask questions. Feel free to ask questions during both lecture and presentations. I think one thing that we should be improving on is that when your classmates are presenting, try to be engaged and try to ask questions. On CampusWire, feel free to ask any questions about the lectures, about the presentations, about the paper, about the homeworks, computer assignments, about anything relevant to security or computer architecture that you find interesting. Feel free to post it there. And try not to just ask questions, try to also answer each other's questions, because that will be also very, very helpful to for you to learn more about the topic. So share your thoughts. Don't be worried if your answer may not be completely accurate. First of all, everything is anonymous, so nobody, including myself, will see who asked those questions or who answered those questions. So just feel free to share your thoughts. We're going to use the reputation points to give out bonus points. Most of the time, you really don't need this bonus points to get a good grade in this class. But if you do, this is the system that we're going to use. The person with the highest reputation points is going to get a lot of bonuses. Okay, and then on CampusWire, the way that you can see your reputation points, if you go to the settings and the members, you will see there's like a number next to your name, and that is your reputation point. And you can actually sort the entire class, I think, and you can see everybody's reputation points, so you can see your relative ranking in the class as well. And another benefit of class participation is, as I said, you can ask questions, stay up to date. And then if you're thinking about, approaching me, talking about, doing research, if you're applying to grad school, I don't know, or PhD programs, you want letters, stuff like that. If I know you, if I see you're active, I will be more than willing to share, to write letters. But if I don't know you, I haven't seen your face, you're not active, then probably I'm going to decline the request and say no. Okay, so this is kind of also something that you may want to consider. So the papers we're going to present, you can optionally read them before or after the paper presentations. I strongly recommend to do that, but you don't need to submit any kind of reading or review or anything like that. So it's just completely optional. But I recommend, so before the day of the paper presentations, take a quick glance at these papers, maybe read them a little bit more. That would be very helpful for you to understand the paper a little bit better. And then once you see the presentations, I definitely recommend you go and read the papers a little bit, in more detail, because that helps you to understand the topic a little bit better. Okay. There will be an exam for this course at the end of week 10. So during the last session of the class, which is the Wednesday of week 10, we won't be able to reschedule it. If you can make it, there's no other option, unfortunately. The exams will be more of like high level kind of questions. We're not going to go really detailed. We might for 1 or 2 questions, but generally the idea is that to make sure that you watch the lectures and you follow along. And then the content that we're going to ask is going to be all the lectures, obviously, and the paper presentations, but not the papers themselves. All the exam will be open book, open note. You can bring your laptop. You can watch lectures during the exam. You can do anything you want, except of course cheating. The format of the exam probably would be multiple choice, some short answers, some open-ended questions. This is the computer architecture class, so we can actually give you a little bit of more empirical questions, like mathematical questions as well. So expect to see some of that. Computer assignments, we're going to have 4, which one of them probably would be optional. So these are all research-oriented programming-based assignments. And the reason that I'm calling it competition or championships is this: they're all based on this thing called championships, which is this kind of think about it as competitions of different sorts that you probably may or may not involve in undergrad or grad school. So essentially the idea is that we're going to ask you to design a system, and we're going to compare each other's kind of metrics, and whoever has the highest going to receive some bonus point or something like that. So there will be a competition among yourself. So the first one, for example, would be about the branch prediction. So we're going to ask you to design a branch predictor. So we're going to give you a trace and ask you to design a branch predictor that has the highest accuracy. Okay. So for example, has, I don't know, like, of course, we're not going to get to 100%, but like closer to 100%. And then we're going to have a scoreboard, and we're going to like list your names and see who's done what. Okay. We're going to give you for all of these championships, for all these computer assignments, we're going to give you the baseline framework code. What you need to do is designing your thing on top of it. So essentially, we will provide a skeleton code and even like a very simple design of, let's say, a branch predictor. What you need to do is designing a better branch predictor. And how you design a branch predictor, that's the question that you need to answer. So this is the researchy aspects of it. You're welcome to kind of like pick any open source design or paper and implement that. Of course, this would be like a one week or 2 week thing. So you're not going to be doing like a crazy new branch predictor, but it's again, as I said, this is a self-motivation class. The more you're interested, you can do more. If you want to do bare minimum, you can do bare minimum as well. But the idea is that if you want to learn more about things, this is your opportunity to learn more about things, okay? So the first one would be about branch predictors. Actually, next week, I'm going to have a full lecture about branch predictors, advanced topics in branch predictors. So once we actually cover that, then you're ready to start the branch predictor championship, which is going to be released next week on Wednesday. The second one will be about designing a cache replacement policy. Again, I'm going to give you a lecture about cache replacement policies, and then you're going to learn what is the state of the art. And then we're going to we're going to give you a framework and say, okay, design a better cache replacement policy. And whoever has the best, we're going to have more points for them. The third one would be optional. Actually would be kind of substitute of your final projects that I'm going to describe as well. So it actually needs to build a real covert channel in a processor. We're going to talk about what is a covert channel and what are the things that you need to consider. But essentially, you have to actually implement a covert channel in your system so that two processes can talk to each other. So we're going to create actually a chat bot that one can send a message and the other one can receive the message. And the fourth one would be about memory scheduling, about DRAM and row buffers. And again, I'm going to talk about what is a memory scheduling. We'll talk about the advanced topics in memory scheduling, and then you have to implement that. These are, these three will be, you have to do all three of them. This fast covert channel one, you may or may not do it, depending on what you want to do. Instead of this third one, you can actually do the final project that I'm going to describe later. Okay? You have to implement everything in C++ because all of these skeleton codes are in C++. Of course, if you want to start from scratch, you can write your own Python code, but you have to write a lot of things if you want to do that, which I don't advise you to do it. But if you want to do, feel free to do it. And as I said, we're going to maintain a scoreboard for every single one of these. And, you get bragging rights if you're finished top. I'm going to consider giving you a little bit of bonus point as well if you finish top. Questions? Yeah.
Bonus will be on top of the assignment mark, or will it be like inclusive of this total?
Say it again.
The bonus will be on top of the assignment, or will it
Yeah. So I mean, as long as you submit your code and your code makes sense, you will receive the full points. The bonus will be on top of that, yes. And again, this is more of like less about the bonus, it's more about you do a good job, you learn more about it. And again, if you're serious about doing some, having a career in computer architecture or security, this would be a good opportunity for you to kind of go a little bit deeper. And then you can always have it in your resume that there's actually, this is very famous, like these championships, if you search, there are many designs actually. So don't be kind of like excited if you find some other designs. Try not to copy them, and then you can technically find any of these branch predictors and submit them. Again, like copying these things are not that difficult. If you want to get by and just submit something, you can. And I'm not gonna go and try to find out what you did. As again, this is more of like a very relaxed class. If you want to learn, you can. If you don't want to learn, just get an A. You can also get an A very easily in this class, okay? So just keep that in mind. And yeah, so this is the scoreboard part. But yeah, it's very exciting. When I was at grad students, I actually did that for a few of them. It's very interesting kind of design, and then you try different things, and some of it may work, some of it may not work. It's a little bit different than implement this, and then boom, right? You can actually do your projects in group of two, because these are design projects, a little bit a little bit researchy, so you can actually find a teammate and do it. You don't need to have the same teammate for all of them. You can change your teammates. I'm not gonna kind of track who is paired with whom. It's on completely your responsibility. So if you have a teammate and your teammate is not participating, your problem. You can submit it individually, you can submit it in team. There's no difference in terms of grading if you do it in team or do it individually. If you're doing it in team, of course, both of you have to submit the same code, so that makes the grading easier for me. Just make sure that list the names of your teammate. And again, if you, for example, your teammate with someone in first CA, you can change your teammate for the second CA. That's fine as well. But just please let your teammate know that you're no longer in the same team with them. If you decide to drop the class, also let your teammates know. So kind of you're try to make sure that you're following. Okay. And make sure that you're not listed under two groups. If you see that, that's where you're not gonna get any points. Okay, so just make sure that doesn't happen. Any questions about the computer assignments?
Professor,
Yeah.
regarding the presentation,
Oh.
for presentation, you're gonna assign us? to
Yes,
do
yes. So you have to,
This-
yeah, you have to submit the Google form.
Okay.
And then if you have a teammate, you can list their name there.
Okay.
And then I'll try to kind of pair you up.
Yeah.
But if you don't, just submit yours. I might pair you up with someone else.
Okay.
Myself. You might also do it individually. I don't know. For computer assignments, you have to find a teammate. Okay. And then try to, easy thing is like, of course, like talk to other people when another good reasons come to class. If you don't know anybody, you can actually post on Campus Fire saying that I'm looking for a teammate, and somebody can message you and kind of like, then you can find a teammate, right? So feel free to do that as well, both for the presentations and for the computer assignments.
Sounds good.
Questions? All right, so there's also a final project. As I said, you can either do this final project or you can do the covert channel part. The final project is that you have to design a simulator, an out-of-order simulator from scratch. This will be basically what we're going to cover in the next few weeks, and we're going to ask you to design that in C or C++, or optionally Python or any other language that you want. We're going to give you the specifications. We're not going to talk, so we're going to talk about lots of features in the next few lectures. Obviously, we're not expecting you to implement all of that, so we're going to give you kind of like a smaller specification, but you need to implement that. And the good thing about the final project is that you technically can start it next week, because you kind of have almost every information that you want. End of next week, you can actually start designing that. It's due in the finals week, end of the finals week, but you have to make sure that you start early because it requires some decent amount of effort. And the fact that it doesn't have a deadline until then doesn't mean that you shouldn't start as early as possible. So you can kind of load balance. So try to work on it maybe on the weeks that you don't have exams and stuff like that. But this is on top of what we have for the computer assignments. If you don't like this one, you can also do the optional CA3, the covert channel. That one also requires decent amount of time. You have to let me know if you're doing that so that we kind of know that, to adjust the deadlines. Okay? Yeah.
Is there starter code for this one, or is it entirely from scratch?
Entirely from scratch. I'm going to give you probably just a very empty code of how you read the input file and what you should produce as the output. But everything else is just, yeah.
C++ is serial, right? But output and execution mostly parallel. So how will we?
So it's no. So I mean, you can still do well. Yeah, I mean, you can design a simulator that mimics the hardware. Well, your function is going to be executed in serially, but in fact, you're going to design every cycle. You kind of implement the whole design. I'm going to give you the examples of how it works. Yeah.
Can you do this one with a partner?
You cannot do this one with a partner, no. So this is individual. Good. Any other questions? All right. The third option is that if you don't want to do the final project, you can also do a research project. This is going to be very rare. If you're doing already research with me, then you can use this option instead of doing the final projects. If you want to do a research with me, you can also reach out and we can talk and see if there's a good angle that you can do. But of course, it's not like, you choose your own projects and do it. You have to first get my confirmation that you can do this, okay? And I'm not expecting that many people will have that option, so maybe 4 or 5 at most. It could be individual or groups as well. If you actually identify a very interesting topic that multiple people can work on it, we can do that. But again, the expectation is that most of you are going to do the final project, okay? So here's the grading. The final project would be 10%, paper presentation 20%, CAs would be 40%. Of course, this is assuming that they're all 4. I need to kind of adjust this when we do the optional one. Exams 30%. There will be some participation points. This is the absolute grading class, so this would be kind of the grade. Almost all of you are gonna give like some form of A or A plus. In some rare cases, you might get an A minus. If you don't really submit things, then that's when you're gonna get a B or C. If you submit everything and you just kind of do a like half decent job in the exam, you will receive either A or A plus. Okay, that's kind of the idea. And again, I'm not gonna kind of track you down to see if you kind of cheated on your projects. But again, if you're not serious about like learning about computer architecture, you can get by getting an A. But I strongly suggest you that you're putting in the time and effort and putting money. Maybe it's a good time to learn about these things because it's an interesting topic. So yeah, try to do that. Yeah.
So if the final project and the computer assignment number 3 are like exclusive.
Yeah, yes.
One, either they like counted twice?
No. So if you do CA3, that would be counted as this 10%. So CA3 alone would be 10%.
Okay, so the other 3 out of 2.
Yeah. So 1, 2, and 4 would be your 40%. 3 or your final project would be your 10%. Good. Any questions? So there are a few other quick notes, reference books, reading material. I'm going to post 2 interesting books that could be helpful for you. It's not going to be, we're not going to based on, we're going to not do, the presentation based on that. So it's more of like extra readings. So it's not really a reference book. There's no discussion sessions. Okay. So just, office hours if you want. If you have questions, just post your questions on Campus Wire. We're going to answer it. If you feel like you need more things to discuss, feel free to reach out to me and then we can talk more. For example, for your computer assignments, if you're not sure what design to use, stuff like that, your first thing to do is posting on Campus Wire and asking for help for other students and me. And then if you want to share something with me, feel free to kind of reach out to my office hours and we can talk, okay? I'm gonna post all the recordings, which means that your voices, not your faces, but your voices would be on these videos. If you have an issue with that, let me know, because I'm gonna post this publicly available on YouTube. And of course, as I said, we are serious about cheating. We are serious about kind of academic dishonesty. So if you caught any sort of like, obvious, cheating, you're going to be reported to, the relevant offices. And again, as I said, this is more of a relaxed grad class and you are here to really learn something. So I think it should do it. All right, so let's have a quick break. And once we come back, I'm going to kind of give you a little bit of like why we're talking about this and things that we're going to talk about. Okay. So let me actually also give you a little bit of motivation of why this would be a good class for you. So the computer architecture, used to be a very hot topic early 2000, but then it kind of like wear off a little bit and then software becomes more interesting. But now with this rise of AI and, hardware for AI, computer architecture is actually kind of rebounding a lot. I mean, of course, software engineering is still a very, very lucrative job, but computer architecture specifically is actually, especially because of, the boom in AI and the reason that, many systems actually require, fast computers to kind of satisfy this massive requirements of data processing, thanks to NVIDIA and others. Being a computer architecture, particularly now, is one of those jobs that you may want to consider actually, because it's one of those areas that, while the other kind of traditional areas in computer systems is kind of, growing down, architecture specifically is actually kind of increasing in demands and the interests of people. And then, if you're following stock market and all, NVIDIA is, significantly improving by day. And again, all NVIDIA really needs these days is good computer architects. So I mean, less important question is, did I buy stocks for NVIDIA? And you might also wonder that given that I'm kind of an computer architecture expert, did I do it? So I did a bit, but not enough, obviously. And also, the fact that I know computer architecture doesn't mean I can predict things in the market, and it's also a very complex market. But hopefully, once you guys become a little bit more experts, you have a better idea about what to buy and what not to buy. So going back to more serious stuff, so what really happens that Harvard becomes again very interesting is that if you actually think about AI, there are three things that kind of AI is AI these days. There is applications or algorithms, there is data, and there is hardware. The algorithms, interestingly, have been around for the longest time. So actually, kind of the idea of neural networks and convolutional neural networks and things like that has been around for a long time, surprisingly. So many of these ideas are actually proposed in early 80s and 90s. That time, nobody really picked them up, and neural network didn't become a thing at that time. But then what happened was, data becomes more prevalent, and this is actually early 2000s, 2010, and mainly because of the internet, firstly, and then second is because of the devices that use internet. So we actually start kind of pumping a lot of data into our systems. We generate a lot of sensors, data, network traffic, and all those things. We took a lot of pictures, we took a lot of videos, and that's kind of the introduction of this massive data sets that then can be kind of fed into these AI machines. Think about this LLMs, large language models, ChatGPT. All it does is basically goes through and kind of like crawling every data that we generated in the internet. 50 years ago, we didn't have that data because we didn't use these machines, right? So there are two things. One is the algorithms, and of course, algorithms improved. Some basic ideas was there. Better researchers work on this, and better algorithms came up, and data was generated. But the real game changer was the hardware, actually. So if you actually look into this kind of interesting graph from this toward data science, this is actually the number of parameters in deep learning models. Okay, so like at the top you will see GPT-3 and Google Switch C and so on and so forth. And as you can see, there's the obvious exponential growth in number of parameters. And if you want to kind of like relate number of parameters to actual computation, you can think about like every parameter requires some form of multiplication and addition. So in other words, if I want to have this like high-end model of, this is, by the way, it's a little bit old. This is just GPT-3, which is kind of now, it's kind of ancient at this point. If I want to have that, I need a hardware mechanism that can actually do this in reasonably fast time. So I need a very, very performant hardware that can do this kind of like receive this stream of very fast stream of data and this massive amount of parameters that I have, and kind of mix them together using matrix multiplication and stuff like that in order to generate the data that I want, right? And what happened was that even 10 years ago, there were no way that we could run something in terms of trillions of parameters in hardware. Like no way, zero chance. And what happens was we came up with these new architectures that allow us to do this kind of parallel processing significantly faster and significantly more efficient. And now we are where we are. And if you, I don't know how many of you have followed this, NVIDIA's recent kind of like, events, GTX, they were talking about the next generation. And then if you actually pay attention to the next generation is like putting these GPUs on some form of a substrate and design something that we call chiplet. And we're actually going to talk about chiplets in the very last week of this class. So there is like, next generation of architecture systems will be built based on these kind of new design strategies, okay? And this is why we are here. And then this is why NVIDIA is growing, by day. Okay, so it's bigger than PayPal and Spotify just one day, because it actually has this capability of building this hardware, and they're continuing to doing that. At least the trajectory shows that they're well in capable of kind of continuing this trend. And of course, as I said, why it's interesting to be computer architecture is because you can be part of this change and can enable this faster computation. So really the trend right now is that we have lots of things that we want to compute, and we really don't have the machine that can compute this for us. If I can't have a machine that can do 100 trillion parameters, I'm sure there could be many. It could fly or could do something very amazing, right? But we cannot do that now. But we are getting to that point, and this is kind of like what is the old research in computer architecture is about at this time. Of course, it hasn't been like this all the time, and most of the things we're going to talk about at the beginning of this class would be more of more traditional techniques that you're using to make things faster, but we are kind of building on top of it until we reach to the point that we're going to talk a little bit about how GPU, for example, does what it does right now. So how do we actually achieve this? That's kind of the question that we're going to answer in this class, especially on the advanced side of things. And then what will happen is that you will see that you're packing a lot of features, a lot of tiny bit of optimizations here and there in order to make this system very, very fast. So what I'm showing here is actually, this is what we call Boom processor. So this is a RISC-V based out of order 4-wide processor. And then in this class, I'm going to actually go over every component of this design. Okay, so I'm going to talk about what is this instruction cache, what is this pre-decode, what is this fetch buffer, decode here, rename, scheduler, what are these, why we need them, and what are the optimizations, what are these newer features that we add to the system in order to make it faster. We're going to talk about this. So we're going to break down each of these components, and we're going to talk about the reasoning behind the decisions that we make. Okay, this will be basically the majority of this class, non-security related. But as I said, what I'm going to show you is that while we are doing what we are doing we should continue doing that. We also need to start thinking about security, because that's kind of stopping us from really adding more features. Because if the system is not secure, then it doesn't matter how fast it is, right? So we need to kind of achieve both at the same time. Okay. So this is kind of like the basic idea of this advanced computer architecture. So how do we actually do that? So as I said, the first thing is you're packing a lot of features, and that's what we're gonna cover in this class. The second thing that's kind of made computer much faster is what I call March-Schwarz spatialization. So this is actually the picture of this most recent M2, or I think this is M2 Apple processors. And what you will see here is that it's a CPU, but there's a whole bunch of other things that also sits next to the CPU. There's this thing called Fabric, there's a GPU, there's a neural engine, there are these DRAMs, and they're also kind of part of these kind of, seems that they're actually part of the same die, so they're no longer kind of separate things. So we're going to talk about how do we actually build these kind of things in a system, and why it matters to build a system like this in your design. But the important things that I want to point out now is the reason that we have faster computers is that we actually pack a lot of these specialized units into our systems. That in the past, we always say that, okay, let's actually build a general purpose unit that can do everything. But then we realized that, oh no, there are actually applications that I want to have specialized design for it. So for example, GPUs initially was there for kind of showing your videos nicely. But people have realized that, oh, there are certain applications such as matrix multiplication or some kernels that you can design your hardware such that they can do this very, very fast, much faster than what your general purpose CPU could do. And then even on top of that, we have these neural engines that are even faster than GPUs in particular cases. So because of this, then we are able to do these things significantly faster. Because of this, we are now able to run massive models even on a small CPU. okay? And then finally, of course, technology had a big chunk, like, had a big role. So this is M3 family, and as you can see, they have this M3, like regular M3, M3 Pro and M3 Max. And the difference between them, of course, there is some architectural differences, but there's actually massive amount of transistors being added, okay? And the reason that we can now pack 92 billion transistors in like a small chip is that we are using this kind of much, much smaller 3 nanometer technology, which is kind of like each transistor is kind of 3 nanometer long. Like 10 years ago, 15 years ago, this was, 48 or 24 or something like that. So we are actually managed to make this transistor smaller and smaller. So then we can pack more of it. And then if you can pack more of it, of course, you can have faster things to do, right? So this is kind of like a very simple analogy. Of course, a little bit complication, but generally, if you can pack things to it, then it will be faster. And then this part is purely hardware and physical design side. We're not going to talk about this part at all in this class. But if you're interested in VLSI design, hardware designs, that's probably something that you can talk about. But you cannot just say that, oh, we did better job at the computer architecture level, and there's nothing to do at the software or hardware layer. I wanted to point out that technology also had a big role in making things much faster. Okay. So we're gonna mainly talk about these advanced features. So they're kind of like the big portion of this class will be talking about these different features. We're going to talk a little bit about specialization. And as I said, in week 10, I'm going to talk a little bit about chipization and how we are actually, how NVIDIA newer generation putting 2 GPUs on this one tiny glass-like thing. How do they do it? And we're going to explain that to you in week 10 as well. Okay. Then we're going to also talk about security a little bit. And as I said, this is an interesting part of it, because for the longest time, we really didn't care about security. We just add features and make computers faster. We were really excited because that kind of create new avenues for us. But unfortunately, now we have realized that we messed up, because now there's this huge bugs in our systems that you cannot really fix easily, because fixing some of these bugs, as we're going to explain in this class, require the whole redesign of your hardware, which is impossible in most cases. So we need to kind of take a step back and to kind of think about what we did and how we should do it correctly. Okay. So it's kind of like 2 things that you're going to see recurring many, many times in this class is that the reason that we have security issues in computer architecture is 2 reasons. The number one is, as I said, we love to add features to our systems. When you add features to your system, what will happen is that your system gets more and more complex, and complexity means bugs, okay? So if you design something very complex, the chances that you're going to introduce some bug in that system very, very high. Probably you've done some, class projects, internship, stuff like that. You start with like tiny, innocent, text editor, you write few codes, things works great. As long as you add a bunch of different functions and put it into your systems, then weird bugs start to show up, right? Exact same thing happens in industry when we are designing these features. When you're adding things and then there's this complex interaction between these different features, then that's when the bug's gonna show up. And we're gonna actually talk about very, very sophisticated bugs that these great minds of researchers kind of found out about them and shared it with the world. And we're gonna talk about them in this class. The second thing that is also a big source of issues is the sharing, okay? So we're going to talk about this thing called side channels, and we're going to show you that the moment that you are sharing things, sharing hardware, then you are making yourself vulnerable to an adversary who can sit next to you, okay? So if you do everything in your isolation, if your system is not connected to anything else, you're not sharing anything with anyone else, then you will be secure most of the time, okay? And that's kind of like the first picture that I showed you at the beginning of this class, was that if you don't give people computers, of course, they will be very safe, right? There won't be any cybersecurity problem if there is no cyber. But the problem is that in order to improve efficiency, in order to improve performance, we need to share, okay? And again, we're going to talk about why we are sharing and what we are sharing. But as you will see that when we are sharing, then the systems become less secure. Okay, so two things, like one is adding complexity and second is adding sharing. These are the two main reasons that the systems, computer architecture systems, are not secure. Okay. And then we're going to talk about, the role of the hardware, the role of the software, and as I said, the security aspect would be mainly the second half of the class. Okay. So let's actually, before jumping into kind of specifics, what I'm going to do for the rest of this lecture is going to give you a little bit of main techniques that we use in computer architecture. Then we're going to start reviewing some basic concepts in order to make sure that everybody is on the same page. And then we're going to start talking about these advanced topics that I said. Okay. So the main techniques that computer architecture is going to use, and you're going to see again this many times in this class, is few main principles. Okay. Interesting things before actually talking about those principles is that computer architecture is kind of a systems problem. So many of these solutions you actually see in your everyday life. So it's not like just about a particular CPU. These are techniques that you can use in your everyday life from going home. Actually, you can use many of these techniques. So what are they? And the first thing is that what we call use abstraction. So computer system is all about abstractions. Software abstract hardware, hardware abstract software, operating system abstracts both. Hardware designer abstract everything on layer above. Software designers has no information about what goes underneath the hardware. So it's all about abstraction, and abstraction works really well because you can only work on the tiny thing, input and output. You don't care where this output goes. You don't care where this input is coming from. All you need to do is that implementing your functionality, right? If you work in these big companies, internships, or full-time, you probably have seen that they're going to give you a function, say that implement this function. Don't ask any question about where this function is going to go. Just you need to design a function that takes this inputs and does this output. That's it. All you need to know is about that, right? So, and then this throughout to like big design, that's the only way that we can survive, because you cannot expect every single software developer in your company to know everything about all the way down to the physics of the design, right? And when we're teaching even, we're going to abstract things away. So we're not going to talk about the software layer or the transistor layer. We're going to just say that, oh, this is the CPU, and the CPU is a machine that takes inputs, instructions, and generate the outputs. So abstraction to make things simple. The second thing that we're going to talk a lot in this course is make common case fast. Okay, so lots of the decisions in computer architecture is that we make the common case fast. We don't care about rare cases. As long as rare cases doesn't have too often, which means that they're not common, we are good. So we're going to talk about things such as branch prediction. And we're going to show you that if I can predict correctly most of the time, I'm going to save a lot of performance. And if I make a mistake, sometimes that's okay. I pay extra penalty, but since it's not a common case, then we are good to go. The third thing is parallelism. We're going to use massive amount of parallelism wherever we can. And you're going to see how this parallelism is going to make things much faster. The main reason that GPU is actually the parallelism that it has. It has massive amount of cores, all of them do the same thing all at the same time. The fourth one is pipelining. So we are actually kind of like do things in sequential steps and overlapping things as much as we can. So we love pipelining as computer architects because it helps us to kind of divide and decouple things from each other, allows us to improve things and make it faster and faster. So pipelining is kind of the go-to option for anything that we do in computer architecture. Fifth thing is like, this is actually the first can of worm, and that is speculation or prediction, okay? So we do this very weird thing is that instead of waiting for things to happen, we just speculate. We make a guess and do something, okay? And then if you figure out that, oh, we made a mistake, we design a mechanism for recovery. But the idea is that if we are guessing things correctly most of the time, then the benefit would be positive, right? So it's overall, I'm saving time by just guessing and doing, especially if it's kind of like a two different kind of like a binary decision of yes or no, or left or right, or taken or not taken. I can pick one and see what happens. if I can design a great predictor, then I'm good to go. And that would be, as I said, your first computer assignments would be something about this. And then the reason that this couldn't be a problem is that we kind of bend a lot of rules when we are doing this speculation, and that's the reason that we're going to have security problems in the hardware as well. We're going to talk about that. Then we're going to another main thing that we are using a lot is having hierarchy. We love to have hierarchy because hierarchy kind of give us the best of all worlds. So if you have a smaller design and a bigger design, if I have hierarchy, then I can have, you know, this, for example, the size of the bigger one, the speed of the smaller one, and so on and so forth. So hierarchy, especially for memory, is a big thing that we at the computer architecture we use. And then finally, using specialization, and this is more of a new thing. So what used to be like, oh, let's make a design as generic as possible that can run all the programs similarly, now completely has changed. And now it's like, what is your application? How can I change my architecture such that it can run that particular application better? So there are hardware for robotics, there are hardware for machine learning, there are hardware for computer vision, there are hardware for quantum computing, there are hardware for X, Y, and Z. And the reason for that is that we realize that we need to actually specialize our hardware to do specific things. That allows to make things much, much faster. And that's kind of like one of the key principles that we are doing these days, okay? So based on these kind of principles, we are really doing this parallelism as much as we can. And we are essentially having this kind of four things that I'm going to briefly discuss: DLP, ILP, TLP, and RLP. DLP is what we call data level parallelism. ILP is instruction level parallelism. TLP is thread level parallelism, and RLP is request level parallelism. Okay, so what are these? So first of all, there's this important things about computer architectures that you have to know, and this is from this guy Flint. He has this taxonomy that you can have different input streams and different data streams and different instruction streams. And depending on which type of configurations that you can have 4 different systems, okay? So you can have what we call a SISTI system. SISTI means that there is single instruction streams and single data streams, which means that one instruction comes, one data comes, we do the computation, and we send the results. That's your regular architecture, the regular CPU, right? A CPU reads one instruction, execute it, go to the next one, go to the next one. This is what we call a SISTI architecture, okay? Then we can have what we call a SIMD architecture. SIMD means single instruction but multiple data, okay? Which means that I have a bunch of different values and I do the same operation on all of them. So for example, I think about matrix multiplication is a great example of SIMD, right? So you have components in your matrix, like a 3 by 3, and then another matrix, and then you multiply all of them. So individually, you multiply each component, but you multiply a 9 component to another 9 component. So this is what we call SIMD architecture. Single instruction, multiple data. The great thing about this is that you get massive parallelism for doing one thing all at the same time. And this is exactly how GPU operates. And some multi-cores actually do the same thing as well. So essentially, you can, if you have like millions of this data, you can add them all together in one cycle. That's how you're going to get like a significant, performance over benefit. Then you can have what we call a MIMD architecture, which is multiple instructions, multiple data. So this is generally the classic multi-core system. This is like what you have in your laptop. You have multiple different tabs open, multiple different applications open. You're doing everything at the same time, each one different instructions, each one different data, but you can do all of them at the same time thanks to the fact that we have multiple cores in our systems, right? So I have a MIMD architecture that allows us to do multitasking essentially. And of course, we can have this weird thing called MIST, which is multiple instruction and single data. And this is a little bit weird because you're essentially saying that I read one thing and I do multiple things on top of it. We usually don't have this, although there are some crypto algorithms, for example, that would use this. So for example, think about encryption, right? So you have a message, you want to do a bunch of different things on that message. That's where you want to have multiple instructions, single data. But in most cases, MIST is not the greatest things to have, and that's not very common to have. But we really love our SSID, SIMD, and MIMD systems, and that's what we usually use a lot. Okay. So now based on this, this different architecture, let's talk about this DLP, ILP, TLP, and RLP. Okay. So the example of DLP is, remember, DLP means data level parallelism. A very simple example of DLP is this, that if you have this would be the last time you will see a gate in this class. So if you have a bunch of bits and you want to add them together, of course you can add them serially. You add them, two of them, the carry kind of ripple to the next one, and then you add another one, the carry goes to another one. But you can have a structure such as carry look ahead cells, which is essentially you get all the 4 bits or all the 8 bits, and then boom, you add them in one cycle together, right? So this is what we call the data level parallelism. So essentially you are doing the same thing at the gate level, at the data level, in order to make things faster. Okay, think about adding an 8-bit versus adding a 32-bit, right? So when you're adding 2 to 32 bits, it's as if you're doing 4 8-bits together. So that's where you're going to get your DLP. We're going to use DLP throughout our design a lot of wherever we can. And this is more at the gate level and the hardware level, which I'm not going to talk most about. But just remember that DLP is the cornerstone of anything that we do. Then we have, ILP, instruction level parallelism, and this is what we talk mostly in a basic computer architecture course, including my M116 course in fall. So we talked about various different things, such as, let's have superscalar, let's have forwarding, let's have pipelining. All those tricks that we talk about in any basic computer architecture class is essentially kind of using instruction level parallelism. If I can run more instructions at the same time, then of course I'm going to get speed, right? So for example, look at this example here. The difference between these two is that if these instructions are kind of dependent to each other versus if here there is no dependency between these instructions, of course I can run all 3 at the same time. But since there's a dependency, I need to run this first and then run this second and run this third, right? And if you remember in your basic computer architecture classes, we talked about various different tricks that you can use in order to make this faster. You can change the register names, you can forward the numbers, you can, pipeline the architecture and stuff like that in order to kind of from this gets to this. And this is all the tricks that we use at the ILP level. We can talk a little bit about this, but these are more of traditional things that we do for computer architecture, okay? And then if you think about pipelining, as I said, this is kind of the way that you showed pipelining in the past. Pipelining you can kind of think about as some form of ILP in some sense, because it's not exactly ILP, but it's some form of ILP in some sense. All right. Then we have what we call thread level parallelism, TLP. And again, this is where this SIMD architectures comes into play. So instead of doing data or instruction at the same time, you just replicate the hardware multiple times and then do the same operation on all of them, right? So think about this what we call processing elements or PEs. Generally, all these architecture accelerators and GPUs, they have tons of these PEs. What they do is that they get all this data together. They do one operation all at the same time. And then essentially they kind of they get the data that they want. And then this is how we make things faster. So you can think about this as a massive DLP in some sense, right? And then you can always, as I said, you can have this multi-core model, which each instruction, each PE doing something separate. So they're not necessarily doing this. But what we get from this is it's kind of still parallelism because now you can run separate things at the same time, so you get multitasking. If I only had this one, then things would have been serialized, which means that if I wanted to, for example, check my email and check my website, I would have do the first thing and then wait and then do the second thing. But now I can do all of them at the same time. I can listen to the music while doing something else and so on and so forth, right? So this is what we call thread level parallelism or TLP. And then lastly, and then by the way, this TLP is what we're going to talk about, here in the class. And then lastly, we have what we call request level parallelism. And this is what all these massive servers and data servers is about, is that the request, tons of requests goes at the same time, and these machines can actually service these requests all at the same time. Think about AWS, think about Microsoft Azure, that you send this request all at the same time. All of us, I don't know, buy a ticket, all of us request a particular service, get an Uber, stuff like that. All of these things are at the request level, and these massive servers can actually kind of like do this activities for us. And then they kind of broke it down into TLP, ILP, and DLP. But at the request level, there are actually these massive systems that can do this. Otherwise, again, things would have been serialized, right? So if you want to buy tickets, I should go first, and then you go next, and then the second person, third person goes after all of us. Versus if I have a massive server that can service the request of all of us all together, then we would have a much faster system. So for TLP, as I said, we're going to talk about this Boom core. This slide you probably have seen before. So there is this difference between various different ways of TLP. So we have normal systems. We have what we call coarse-grained multi-threading. We have what we call fine-grained multi-threading, and then we have simultaneous multi-threading. So kind of normal, CMT, FMT, and SMT. So what is the difference? So in a normal system that has only one thread, if I have a bunch of different applications, let's say I have a green application, a gray application, a yellow application, and red application, I would kind of serialize, run them in a serial mode, right? I run the first one, then I switch to the second one, then I switch to the third one, right? So this is what we usually call context switch. So run first one for some time, context switch to the second one, context switch to the third one, okay? So this is what the normal system would do. What I can do now is that if I have the capability of running 4 things at the same time, then I can start combining these things together, right? So what I could do is essentially I can do these things called multi-threading, okay? That I can use multiple of these applications running at the same time. The simplest one is what we call coarse-grained multi-threading, which the difference between the regular processor and coarse-grained is I can quickly switch between different applications. I don't pay that much of a penalty for not doing anything. So at this point, I didn't do anything because I need to context switch. With the coarse-grained, I can quickly switch back and forth between applications seamlessly, okay? This is called CMT. But CMT is also not that efficient because, for example, look at these kind of like 4 different lanes. This green lanes means I'm using it. This white lanes means that I'm not using it. So what happened? So what I could do instead is that I can do something like this. This is what we call a fine-grained multi-threading, that at every cycle I can run one application at a time, and then I can switch. And then the ultimate version is what we call SMT, or simultaneous multi-threading. Let's say if I have 4 workers, I don't care where the request comes from. I just feed as much as we can into this. So if I have a bunch of different processes, all I care about is that, do I have resources to run any part of any of these applications? And as you can see, this basically becomes the kind of mixture of all these applications running at the same time. So your processor really not just running one application at a time, it's running a bunch of different applications all at the same time. And this is what we call an SMT. And this is the standard in all of these systems that we have. You probably have heard about hyper-threading. It's the same thing as SMT. Intel uses different words for it. But this is what we do now, that we don't do just one application. We don't switch between applications. We run all of them. So in your pipeline processor, you have a bunch of different applications running at the same time. And as I'm going to talk about in the Boom core, for example, you will see that this is a bunch of different instructions. So these are coming from different applications. And we have to design our systems, be aware of this fact, okay? But again, you probably can guess that when I'm mixing these things, remember I told you that the second reason that we have all these problems is the sharing. And this is the worst nightmare in terms of security, because you're essentially sharing everything all together. And of course, if one of these, if this red one is, for example, an adversarial process, they have very, very strong capability to read things off of these other processes. And we're going to show you how this is possible. But we really love this because this gives you extreme amount of efficiency and speed. So this kind of trade-off that we need to deal with, okay? So, and then RLP I already talked about. There's also one that's called ALP, and this is kind of accelerator level parallelism. So, for example, think about your CPU and GPU, right? So you take an application, you instead of running it on your CPU, you offload it on your GPU. This is what we call an accelerator level parallelism, but you can think about as kind of a subset of TLP. So TLP is basically saying that you have multiple threads running at the same time. If you consider that these threads could run either on the CPU or on the accelerator or GPU, then ALP is kind of some form of TLP, or you can consider it as a separate things if you want to, okay? All right, so based on this, let me see how many more do we have. Okay, now I'm the end of it. So based on this, in the next lecture, I'm going to first talk about basics of, a pipeline structure, okay? Like what is fetch, decode, stuff like that. And then how we do it for a very simple processor. This is what we did for our undergrad computer architecture course. So I'm going to just very quickly go over like very basic principles that we did there and the basic design of that. Then I'm going to go through this very, very complex system. I'm going to talk about these individuals. Week 2, we're going to be talking about this front end part, which is fetch and decode. Week 3 would be about this execution part, which is doing ROBs and also all scheduling and all those things. And then week 4 onwards, we'd be talking about memory hierarchy. And then we're going to talk about the security parts. All right. Review the content of M16 if you want to, and wait until Wednesday to see if there's like things that you need to know. There are also some other courses that might be helpful for you to kind of like look at. At end of every lecture, I usually add acknowledgements. Take a look at them. It would be useful information. All right. So see you guys on Wednesday.